Hi, hello. I hope to find you well. My name is iysaouy, and I'm gonna talk to you about modeling and performance improvement of PV array configurations under partial shading conditions to overcome the mismatching power losses. Currently, PhD students in Smart Communications Research Team, formerly known as LEC, and the Research Center ISSS at Mohammedia School of Engineering of Mohammed V University in Rabat, and in Laboratory of Signal Systems and Components of Sidi Mohammed bin Abdullah University in Fez, Morocco. My research interests includes the control of power electronics for renewable energy systems, especially for photovoltaic systems, grid integration, reliability in power electronics, and harmonics identification and mitigation in grid-connected power converters. Also, I'm a member of IEEE and IEEE Power Electronics Society and IEEE Power Electronics Society Young Professionals. My presentation will start with an answer on the following question. Why do we need renewable energy? Then we will give some information about solar energy and then state of art on mismatch problems and then PV array configurations followed by partial shading and then resultant discussions and I will done with some conclusions. Why we need renewable energy? So thousands of years we have relied on burning fossil fuels to generate energy. But in today's world, using oil, gas, and coal for our energy needs is becoming a problem. Climate change is one of the greatest environmental challenges that we have ever faced. And the main cause behind it is our dependence on fossil fuels. The answer to all of these problems, renewable energy, energy such as solar energy, wind energy, and water power, is generated from natural energy sources. And unlike fossil fuels, these sources of energy never run out. With a much lower impact on the environment, using renewable energy helps to protect our planet by significantly reducing the amount of carbon emissions that we produce. But using renewable energy sources, we also reduce our dependence on fossil fuels, gas, and oil reserves, which means that we can avoid the rising cost of energy bills and improve our energy security. In order to preserve our planet, our wallet, and our energy sources, we all need to be involved in switching to renewable energy sources and making our home more energy efficient. Among these renewable energies, we can find solar energy that is energy captured from the sun that is converted into thermal or electrical energy. Solar energy is the cleanest and most abundant renewable energy source available. There are several ways to harness solar energy. Photovoltaic, solar heating and cooling, and concentrating solar power. Solar energy is a flexible energy technology. It can be built as distributed generation or as a central station, utility scale solar power plant. Some of the major applications of solar energy are as follows. The energy obtained through photovoltaic generators and their applications is greatly diverse. If a general classification is established, it can be said that it's divided into large sections. Isolated systems, grid connections. Isolated systems such as telecommunications, agriculture applications, street lighting, rural development, and so on. The second largest group of the photovoltaic systems are those connected to the electricity grid. Systems connected to the electricity grid, it is one of the latest and the most innovative applications of the photovoltaic systems, consisting of the installation of a photovoltaic field and inverter, capable of transforming the energy supplied by the panels and pumping it into the electricity grid. Now we will move on to the mismatch problems that occur due to the many variables, including manufacturing variance, partial shading, thermal gradients within an array, and even surface soiling, cloud shading, and edge effects, field bypass diodes, voltage drop in conductors, variable cell degradation, and accumulated model wear and tear. But we have focused in this work just on the partial shading that could be created from clouds, snow, birds droppings that reduce the productivity of PV models.
and increase the power losses in the entire PV array. In order to study the effects of partial shading on PV system, we have to define first some solar terms. As you see here in this slide, we have drawing of the cell, the model, and the array. The PV cell is the basic unit in a PV system. An individual PV cell typically produces between 1 and 2 watts, hardly enough power for the great majority of applications. But you can increase the power by connecting cells together to form larger units called modules. Modules in turn can be connected to form even larger units known as array, which can be interconnected for more power, and so on. In this way, you can build a PV system to meet almost any power needs, to matter how small or great. I have used in this work the model 2 diode to represent a PV cell. A PV cell is modeled as a current source shunted with 2 diode and represented by an equivalent circuit as shown here in this slide. The equation relating the output current and the voltage of a PV cell at insulation G can be written as shown here in this slide. The specification of the model used at standard test conditions are shown in this slide. Fortunately, there are a number of different approaches that can be applied in a PV system designed to reduce shading losses. This include the use of different stringing arrangements, bypass diode, and inverters. But we have used here in this work the PV array configurations to overcome this problem of partial shading. So for that, a matrix of a 9 by 9 PV array connected the NTCT configuration as shown here in this slide, considered for the study. A TCT configuration is obtained from the simple series parallel configuration by connecting cross seats across each row of junctions. All the models in a column are connected in series and each model in a row has models connected in parallel. The PV array consisted of 81 models with 9 rows and 9 columns. Another type of PV array configuration is called a magic square. A magic square is n by n square grid filled with distinct positive integers in the range 1 to n square, such that each cell contains a different integer, and the sum of the integers in each row, column, and diagonal is equal. The sum is called the magic constant or magic sum of the magic square. A magic square view pattern shown in the figure is chosen for the study to show that magic square view configuration enhanced PV power generation. The models in the total cross seats configuration, as shown in precedent slide, are rearranged according to chosen puzzle pattern and is shown in here in slide. Here, the electrical connection of the models remains the same as indicated in figure. However, the physical location of the models is changed. Thus, the magic square view arrangement increases the current in iron anode under partial shading conditions and minimizes the bypassing of panels. Hence, the power generated by the array for the same shading pattern is increased. To verify the proposed technique for different shading conditions, namely short-wide, short-narrow, long-wide, long-narrow, are considered. But here we have studied just long-wide pattern. The shading conditions are defined based on the number of shaded columns and shaded models per column. The PV characteristics are obtained for each shading condition for both TCT and magic square view configurations. To study this partial shading scenario, a PV array with 4 distinct groups according to the insulation level is considered. The group 1 receives an insulation of 900, while group 2, group 3, and group 4 receives an insulation of 600, 400, and 200 watts by meter square, respectively. And shading pattern is shown in here in figure. The same shading pattern is applied to the magic square view configuration, as shown in here in this figure. It is clear that the CT topology in row 8 and 9 are bypassed to extract the maximum power from this PV array. However, in the magic square view topology, the maximum power occur corresponding to the nominal voltage of the array. Now we will move on to the resultant discussion. The PV characteristics corresponding to this array is shown in this figure. The maximum power generated by the array in the TCT configuration is 3099 watts. After rearranging the models according to the magic square view pattern, the power generated by the array is increased by 34%. Thus, arranging the models according to the magic square view pattern increases the power produced from the array. As seen from the figure, the power generated by the magic square view arrangements is higher compared to total cross-state arrangements. The conclusions in this magic square view configuration as a one-time arrangement for the PV models in array demonstrates the improvements in PV power generation under partial shading conditions. In this approach, the physical location of the PV models in PV array is according to the magic square view pattern without alternate electrical connection. The magic square view spread the effect of shading over the array and reduces the predominant shading of the models in one row, thereby increasing the generated PV power. The performance of the system is studied for the long wide shading pattern, but in this work it is revealed that positioning the model in PV array according to magic square view pattern shows better performance under partial shaded conditions. And thank you for your interest.